Hi everybody, my name is Qiyu Wan. Today I'm glad to share my work about Fast-BCNN, massive neural skipping in Bayesian convolutional neural networks. Recent years we have witnessed a tremendous success in the field of machine learning. We see machines are achieving human levels or even better in some complex games like Go and Pac-Man. However, as the Dr. Stuart Russell said, the real world is much bigger and much more complex than Go board. As the AI systems are being used in various domains in our society, such as auto-driving, medical diagnosis, and smart home. When the system comes into an unfamiliar situation or being attacked, it may probably fail to make right decisions, which may have huge consequences to our society. Therefore, it's very important to safely and reliably deploy machine learning in high-stakes scenarios. Bayesian method has emerged as a promising solution to improve the robustness of machine learning. For a general NN model, it can identify the input if the model is well trained on it. But once the model meets an unfamiliar one, it may give a wrong prediction. Now, if we have a Bayesian NN model, where the weights are all following some certain distributions, the input will go through the model multiple times, while each time different weights will be sampled from a distribution. As a result, the output will also become a probabilistic distribution. This distribution indicates how confident you are about your decision. Here, for example, the comparable probabilities indicates the prediction may be wrong, so that we can abandon this result to avoid the mistake. As one of the most popular Bayesian learning models, Bayesian convolutional neural networks replace the Gaussian distribution in traditional Bayesian NN models with Bernoulli distribution, so that it can be implemented by adding a dropout layer after each convolutional layer in normal CNNs. As a result, there are redundant dropout layers exist in BCNN. Another important feature is Monte Carlo dropout process during BCNN inference. Each forward pass, the weights will be sampled from Bernoulli distribution, which can be interpreted as turning on dropout. This stochastic process will be repeated multiple times and finally produce an output distribution. Although the output distribution can provide us a robust decision making, it requires BCNN to conduct many sample inferences. When we compare the inference process of CNN and BCNN on both GPU and FPGA, a huge increase can be observed in terms of execution time and energy consumption. Therefore, we need a fast and efficient execution for BCNN inference. So far, I have talked about the introduction and the motivation. Next, I will introduce our Faster Pcr design. We first unveil two types of invalid neurons in BCNN inference. The first one is drop neurons. These neurons are set to be zero in the dropout layer, like the green-colored neurons here. The ratio of dropped neurons is determined by the drop rate from 10 to 50%. The second type of neuron is unaffected neurons. Here is a simple example to explain what is an unaffected neuron. In the first case, the dropout is turned off, so that the values in the dropout mask are all ones. No inputs are dropped. We get a zero-valued output after the ReLU function. In the second case, the dropout is turned on. We see two inputs are dropped. Since their corresponding weights are negative, they should have produced a negative product. Because now they are dropped, so the output tends to approaching positive. However, due to the ReLU function, output value still remains zero. Such neuron is defined as unaffected neurons, as they are not affected by the dropout mask. In the third case, when three inputs are dropped, the output finally becomes positive, which is affected by the mask. We observe a large amount of unaffected neurons in feature maps, averagely about 50%. Obviously, the computations for both types of embedded neurons is unnecessary. Overall, we estimate that 60 to 75% neurons can be skipped. Then, we propose the skip-based execution flow. In a normal execution, all neurons should be computed no matter they are invalid or valid, because we don't know it. In a skip-based execution, we pre-identify the invalid neurons among them and only calculate the valid neurons. As a result, the memory access and computations for invalid neurons are totally eliminated. To identify the unaffected neurons, we leverage the unique feature in the ReLU function. First, we define the NW input as those inputs who have negative weight partner, as they together generate a negative product. Dropping more NW inputs means that the output will be approaching positive, but the ReLU function keeps it at 0 until it really becomes positive. Only when the number of dropped NW input, ND, reaching a large magnitude, the output neuron will become affected. The following animation explains how ND impacts the neuron as affected or not. Finally, we propose the following criterion to identify those unaffected neurons. Once we can pre-identify the invalid neurons, we leverage the information of dropout mask and neuron location to classify the current neuron as valid or not. If it's valid, we skip to the next neuron, and all computation for this neuron are saved. If it's valid, we normally execute the calculation. As we know, the inference is highly parallelized among the processing elements in modern architectures. The issue is that the current CNN data flow cannot efficiently support our skipping strategy. Thus, a more efficient parallelism scheme is required. To solve the above problem, we propose skip-friendly parallelism. We first investigate the original neuron parallelism. This method maps the neurons in the same channel into PE arrays, which will cause some PEs become idle if their corresponding neurons are invalid. To avoid this idleness, we design an independent neuron parallelism, where PE can skip to process the neurons in the next channel. However, this requires to store all the weights in different channels in on-chip buffer and duplicate them among the PEs. Here, the memory overhead equals to the size of the PE array. The second parallelism we analyzed is called feature map parallelism, where the neurons along the depth dimension are mapped into the PE arrays. Similarly, the invalid neurons incurs PE idleness. In the independent feature map parallelism, PE can skip to the neuron in the next position. This also brings extra memory overhead to store the inputs. But given the same hardware parameters, this scheme comes at less cost compared with independent neuron parallelism. So we finally deploy the independent feature map parallelism into our hardware implementation. The overall architecture of Faster Pcr includes a group of PEs, a central controller, a central predictor, and off-chip DRAM. Each PE consists of 3 parts: a Bernoulli random number generator, a convolutional unit, and a prediction unit. The convolution unit does the essential computations. It operates normally in the first non-dropout inference. In the following sample inference, the first layer gets a shortcut for extremely fast execution, and the rest layers will be in skip mode, where the skip engine fetches the corresponding input based on the job bits and prediction bits. Prediction unit is designed to count the number of job NW inputs. To reduce the design overhead of the overall system, the prediction unit is implemented to be a lightweight module. The key part of the prediction operation is realized by an AND gate array and a counter array. Instead of storing the index of all negative weights, we use indicator bit to represent the polarity of weights and transform the counting process into one-bit convolution, which can be easily achieved by an AND gate and a counter. Here, the choice of Tm prime is related to the synchronization issues. Since the prediction unit is responsible to provide prediction information to convolution unit for the next layer execution, the execution time of prediction unit should be less than the convolutional unit. And this is based on how many counting lengths we use. Our analysis shows the required number of counting lengths Tm prime is small and the overhead is strictly limited. In our evaluation part, we conduct the experiment on Xilinx FPGA platform. 3 types of popular Bayesian networks are evaluated. Our design space covered a baseline CNN accelerator without skipping strategy, and 4 types of Fast-BCNN with different Tm and Tm prime. For 3 types of benchmarks, averagely 2 to 8 times speed up and 40 to 80% energy reduction are achieved when we compare Fast-BCNN with baseline under negligible accuracy loss. We also found the best hardware configurations in the design space whose Tm equals to 64. Furthermore, the energy result shows that our prediction overhead is rather small. We further compare Fast-BCNN with conventional sparse CNN accelerators, CNV routine, even the same computation resources. Different from CNV routine, we target on skipping the entire computations for output neurons, and the experimental result shows our design achieves small speed up and energy saving. Dropout approximation for Bayesian deep learning has been developed early in 2016 by Yarin Gao. It's very popular in machine learning society because it's easy to implement. In our community, hardware acceleration for Bayesian neural networks are not well studied. Tsai proposed the first work to efficiently sample Gaussian random numbers on hardware to accelerate the BCNN inference. There are some modern CNN accelerators employ this skipping strategy, but they are fundamentally different from our method. There are also some work discussing the CNN data flow, which inspired us in developing the skip-based parallelism scheme. Generally speaking, we propose the first work that targets on accelerating BCNN inference by skipping redundant computations for 2 types of neurons during repeated BCNN inference. In conclusion, we characterize 2 types of embedded neurons existing in BCNN inference, whose computation can be potentially skipped during runtime. We then propose Fast-BCNN, an FPGA-based accelerator furnished with a flexible parallelism scheme. Thirdly, we design a group of unique processing elements to accommodate the parallel operation of convolution and prediction unit. Lastly, our experimental results demonstrate our design achieves 2 to 8 times speed up and 40 to 80% energy reduction over baseline CNN accelerator without skipping strategy. That's all for my work. Thank you for listening.